For the first time in history, we are bringing Conditional Gaussian Simulation to QGIS. The integration of our scripts into QGIS is the engine driving this extraordinary advancement. Our data now sings a new tune, unveiling hidden patterns thanks to this tool perfectly integrated into QGIS. Join us as we embark on this unprecedented journey, reshaping the geospatial landscape with QGIS. Hello and welcome back to the Conditional Gaussian Simulation course. My name is Marcel and I'm the main instructor of this course. This is the fourth lesson of the course, and today we are implementing Conditional Gaussian Simulation into QGIS. In addition, we are going to analyze the results of the executed Conditional Gaussian simulations. Let's start. For those who wish to gain full access to the course, please visit the GeoRGB community website at thiscourse.online. Then go to the Conditional Gaussian Simulation course for environmental projects, get enrolled in the course, and then you will be ready to start learning. Here, as you can see, we already loaded several lessons. We have the introduction to the course. We have the lesson 1 that is about Gaussian anamorphosis, in total almost 1 hour of content. Lesson 2 that is about simple Kriging. In this lesson, what we did is the exploratory data analysis, the variography analysis. We created also the grid for the interpolation, and at the end we performed the simple Kriging. As you can see, this video lesson has 1 hour and a half of content. In lesson 3, what we did, it was the Kriging analysis model. Then in this lesson, we explain why sometimes the simple Kriging or the ordinary Kriging is not the best method to predict the values at the unsampled locations. And in lesson 4, that is the lesson for today, we are implementing Conditional Gaussian Simulation into QGIS. And this lesson represents 1 hour and a half of content. Also here you have an overview about the lesson, and in exercise files, you can download here all the scripts that we are using during the lesson. Also, you can follow us in the YouTube channel. Here you have all the content that we are adding on the website, but here there are some restrictions. However, you can follow the lessons perfectly just watching the video tutorials on YouTube. Before performing any Conditional Gaussian simulation, we have to complete 4 different steps. These steps are the exploratory data analysis, the variography or structural analysis, the creation of the interpolation grid for the estimation and or simulation, and the last one, the estimation using the simple Kriging. In today's lessons, we are not going to be talking about these 4 topics. As I said at the introduction, I want to be focused on the integration of the Conditional Gaussian Simulation into QGIS, and also at the end we are going to analyze the results of the Conditional Gaussian simulations. But just as a friendly reminder, I would like to tell you that we was talking about these 4 topics in the previous lessons of this course. For example, in the first lesson, we was talking about Gaussian anamorphosis, where we transformed the data to a perfect Gaussian distribution. Also, in the second lesson, we was talking about the exploratory data analysis. We did the variography analysis. We created the grid interpolation, and also we performed the simple Kriging. At this point, I would like to make a definition about the Conditional Gaussian Simulation, and we are going to explain term by term, starting with conditional. The term conditional refers to the fact that these simulations are based on given or conditioned information. In the context of spatial statistics or geostatistics, we often have some data at certain location, and we are interested in predicting what may happen at other unobserved locations. These simulations are conditional on the information we already have. These pre-existing data points are used as a conditions for the model to generate the simulations. In our case, we have the Muse River dataset. That is these red dots over here. Let me take all the layers and select this one. And we want to use this data to create our model based on the simulations. But as you can see in the attribute table, this data has information here that in our case is the Gaussian anamorphosis of the original data set. Then we want to use this information in order to create the new model based on the simulations. In the opposite case, we are going to be talking about unconditional Gaussian simulation, where we are going to take in consideration the information that we have in our data set, but we are not going to take in consideration the exact location of our data set. And that's the main difference between conditional and unconditional. Both of them are going to reproduce the statistics and the spatial structure of the data, but one is going to take in consideration the location of our data set, and the other one is not going to take that in consideration. Now it's time to talk about the Gaussian term. Gaussian refers to the statistical distribution that is assumed for the simulations. Specifically, a Gaussian distribution is a specific type of continuous probability distribution for a real value random variable, also known as a normal distribution. It is defined by two parameters: the mean, that is the average, and the variance, that is a measure of a spread or dispersion. The Gaussian distribution is often used in statistical modeling due to its nice mathematical properties and because many natural phenomena and measurement errors follow a distribution that is approximately Gaussian. The last term is the simulation. Simulation refers to the creation of a representation of a system or situation. In this context, the simulation is a computational algorithm that produces data that mimics some stochastic process or distribution. By simulating data, we can understand the potential behavior and variability of the system being studied. Conditional Gaussian simulations, for example, will generate many possible realizations of the spatial distribution of a variable, given the data we have and assuming a Gaussian distribution. Now let's go to move on and start with the conditional Gaussian simulation. And first, let's go to create a single simulation. Then we are going to create a new R script. Click here. I'm going to paste the script I created. And now we can analyze a little bit this script. All this section over here is for the interface that we are going to get on QGIS. This is the libraries that we are going to use from R. And this is the models that I selected that we can use for to fit on the data related with the semi-variogram. This one is to load the grid that we created already on the second lesson. That's the interpolation grid. This one is to give a spatial structure to that grid. The next one is to assign the reference coordinate systems. The next one is to define the parameter that we are going to use to do the simulation. Here we have the semi-variogram. We need to have the data. This data will come from the variography analysis. Also, this is related with the model that we fit on the semi-variogram. That's the model that we are going to use to create the simple Kriging, but also the data that we are going to use to do the simulations. And this line over here is to create the simulation with the interpolation grid. This one is to create the final raster with the results of that simulation. And all this over here is just to create an spreadsheet with the information of each value for the pixel for the simulation. Then here we are going to have a spreadsheet where we are going to have the coordinates for each pixel in our grid interpolation, and we are going to have the value for the simulation. It is interesting to see that the script that we are using for the simulation is the same as the one that we are using for the simple Kriging. The only difference is in this script, we are adding here the number of simulations. Then when you are adding this new parameter, it is indicating that you want to do simulations, okay? Also here we have the mean value for our data set. And also another very important thing in this script is that we have to add this parameter, the maximum number of samples that we want to use for the simulation. If you don't add this parameter over here, the simulation is not going to work. And what it means, okay, let me show you here on the map. Have this one here. Then the number of samples is the number of samples that we have, is our data set, or maybe the number of measurements we have. And it is related to the range, right? After completing the variography analysis, we know what is the range of the spatial correlation data. For example, if the range, let's go to take this tool over here that calculates the distance. For example, if we have a range of, let's go to see, around 1,000, when we make a circle of 1,000 meters, we're going to have all these data points. Then we want to specify in that parameter how many samples we want to use to create our simulation. In general, if you don't have too much samples, like in this case, the density of the samples is not really big, you want to use all the data inside of the range. But if you have a lot of data inside of your range, the computational time is going to be very big. Then maybe you want to reduce the number of samples that you are using for the simulation. But in this case, as you can see, the range in this case is around 1,000, and there is not too much samples, right? Then you can put, for example, in this case, 100, because here inside of this range, if you make a circle that has a radius of 1,000, you are not going to have more than 100 samples. Then in that case, you are going to guarantee that you are using the maximum number of samples for the simulation. And that's what that parameters mean over here. The maximum number of samples or measurements that you want to use for your simulation. The number of simulations is not going to be an option. Then here is going to be just one, because this script is just for one simulation. And also here we can remove the option for the number of simulations, because as I said, it's not an option in this script. Then we can take this one out. And for the mean value of the data, in our case, it's going to be 0, because with the Gaussian anamorphosis, we force the data to have a mean value of 0 and a standard deviation of 1. But if you are using a different kind of transformation, you have to make sure that you are putting here the value according to the mean of your data. Also, you can here, put this value here in the interface if you want to put what is the value of the mean, right, as an option, or just modify directly the script over here. In addition, this script is only working for a omnidirectional semi-variogram. If you want to apply any specific direction, you have to make the modification here on the semi-variogram, because this one is not working for directional, it's just for the omnidirectional one. There are a lot of modifications that you can do on the script to adapt this script to the data that you are using, okay? And that's the things I did for this specific example. Now we can save this script with this name, single simulation. I'm going to cut this one here, remove these two rows, and press this button here to save the script as. I'm going to save in the file folder with this name, then save, and I can close this one here. Now we can go to R, select the folder simulation, and here we have the new script that I make a mistake because here is not saying single, but that's okay, I can fix it later. Then double click to open, and here we have the interface for this new script. Now let's go to add all the information to execute the conditional Gaussian simulation. Layer has to be the step number 1, because in the step number 1, we did the transformation from the original data to the Gaussian anamorphosis that was completed in the lesson 1 of the conditional Gaussian simulation course. Let me show you here at the attribute table. Here we have the original values for the zinc concentration in ppm, and here we have the Gaussian anamorphosis transformation values. In total, we have 155 samples. It is fundamental to have our data with a perfect Gaussian distribution before to apply any conditional Gaussian simulation. Remember that we pass from the original data. This one here is the histogram for the original data. Here we have the same information but with the box plot, and also the outliers and the mean value and the median. Then we did the Gaussian anamorphosis transformation, and we pass from this distribution to this distribution. This distribution is the same histogram that we have over here, where we can see that we have a perfect Gaussian distribution with a mean of 0, median of 0, and a standard deviation of 1, indicating that the data that we get after completing the Gaussian anamorphosis is valid to perform the conditional Gaussian simulation. The next thing that we have to do is to add the parameter that we want to do the simulation. In this case is Gaussian transformation, is that parameter that I show you over here, this parameter over here. Now what we have to add is the cutoff, the lag distance, the Nagra effect, the model that we are going to use, the range, and the partial seal. All these parameters are related with the variography analysis, and that analysis was already completed in the second lesson of the conditional Gaussian simulation course. And we are going to use that data to fill all this data in the interface. In the variography analysis, we decided that the best cutoff it was 1,250 meters, the lag distance 100 meters, and for the model, we get the next results. These ones over here. Then we can use the same information. The model is going to be the spherical one. The Nagra effect is going to be 0.10. The partial seal is going to be 1.29. And the range is going to be 1,176.12. Then let's go to add that information on the script. This one here is going to be 0.10. Model is going to be the spherical one. Range is 1176.12. and the partial seal is 1.29. Next, we want to add the grid location. This grid is where we are going to perform the simulation. And this grid also was created in the second lesson. And if we take this one out, and let's take this one out and also this one here, we can see the grid is this one over here. At the end, what we have with the grid points is the unsampled locations. Each of these gray points is one unsampled location. And for each unsampled location, we are going to simulate one value if we are doing just one simulation. But if we are doing more simulations, for example, if we are doing 10 simulations, for each unsampled location, we are going to simulate 10 different values. Then with all this information, we are going to create a raster. And that raster is going to have a pixel dimension of 40 by 40. And in each pixel, we are going to have the same information that we have for these gray dots, but just in a raster file, because this one is a vectorial file. The advantage of having a raster file is that provides the information in a continuous way. But when we have a vector file, what we have is the information just in a specific point. And that's the difference. Then let's go to add the grid location. That is the CSV file with the grid points. That one is here. Again, we created this file at the second lesson of the Conditional Gaussian Simulation course. If you want to know how to do that grid, just watch that video tutorial. The maximum number of samples is the samples that we want to use from the data set to do the simulation. In this case, as I said previously, we are going to use 100 samples. As we don't have a big density of samples, that is the red dots, we want to use all the samples that are contained in our range. Remember that in our case, the range is 1,176. That is going to be the radius of the range. Then you have to make a circle and take all the samples inside that circle. And I guess with 100, we are covering all the samples inside that range. Even you can add 150, it doesn't matter, right? At the end, in this case, the software is going to take all the samples inside that range. For example, if the total samples inside that range is 80 samples, the software is going to use 80 samples to do the simulation. It's not going to take 150 because there is no 150. But I put 150 in order to guarantee to use all the samples inside that range. Remember that the Muse River dataset has in total 155 samples. Another important thing is I'm saying all the time the samples that are inside the circle. We are assuming that is a circle because we was using the omnidirectional semivariogram. When we are using the omnidirectional semivariogram, we are assuming that in all directions we have the same spatial continuity. The spatial continuity in this case is going to be isotropic. But if you have one specific direction where the spatial continuity is longer, then you are not going to have a circle. You are going to have an ellipsoid. And that situation is going to be different. Then you want to take the samples contained inside that ellipsoid. But that is a little bit more complicated and is a case where we have to work with directional semivariograms, and we are assuming that the spatial continuity is anisotropic. That's a different case, and we are not going to be studying that case in this course. The next thing is where we want to save the final raster. Then here we can click Save the File, and I'm going to create a folder here in Simulation, new folder, that is going to be rasters. and I'm going to save inside this folder. And that one is going to be called as a single simulation. Save, and also I want to save the spreadsheet. In this case, after completing the simulation, the script is going to create a spreadsheet. In that spreadsheet, we are going to have the values for the simulation for each of the unsampled locations. Then I'm going to select a folder here. In simulations, I'm going to create a new folder that is going to be dataset. And I'm going to save inside here. And this one is going to be a step 2 simulation. This spreadsheet is really important because later we're going to use this spreadsheet to revert the Gaussian anamorphosis to the original scale. In addition, the information contained inside of this spreadsheet is very, very, very important because it's going to help us to evaluate if the simulations are good. Let's go deeper in this concept. In the process of conditional Gaussian simulation, the goal is to generate simulated maps or realizations that are consistent with the observed data and replicate the same statistical properties and spatial correlations. Here is a summary of how this happens. First, respect for observed data. The simulations are conditional on the observed data, meaning that the simulated values at sample locations are set to the observed values. This ensures that each realization is consistent with the available data. Second, replication of statistical properties. The simulations aim to reproduce the histogram frequency distribution of the observed data. This is typically ensured by drawing simulated values from a Gaussian distribution, as this is a commonly observed distribution in the nature phenomena. Third, replication of spatial correlation. Spatial correlation is characterized by the variogram, which describes how the data is correlated in the space. For example, how similar or dissimilar values are as function of the distance. The simulations aim to replicate the variogram of the observed data. This is typically ensured by the method of simulation. For example, in conditional Gaussian simulation, simulated values are drawn from local conditional distributions that account for values and locations of nearby previously simulated or observed points. By satisfying the 3 previously points, the simulated realizations provides a suite of possible scenarios that are statistically and spatially consistent with the observed data. They reflect the nature, variability, and uncertainty of the phenomenon under study, offering valuable insights for decision-making processes. Now you really know the importance of having this spreadsheet, just to analyze the results that we get with the simulation. Then save. Now that everything was filled properly, we are ready to run our first conditional Gaussian simulation. As you can see in the screen, we have printed the model with the Niagara effect, with the model that we are using, the spherical one, with the partial seal, and also here the range. And as you can see over here, it is saying using conditional Gaussian simulation. Then we can close these windows. This script generates 2 different files. One is the raster, and the other one is the spreadsheet. We can open the attribute table. But this spreadsheet and also the raster are saved in the folder. If we go to the folder, is this folder here, open the rasters, we have the raster saved here, but also we have the spreadsheet saved here at the dataset folder. We can open the spreadsheet with Open Office, okay? And here what we have is the X and Y coordinates for each pixel in our raster, and also the values for the simulation. The first route is just for the head. Then in total we have 3,153 pixels in our raster, and the number of pixels is the same number of points that we have in our grid. These gray points, then if we go here to the attribute table, you are going to see that here we have the same number of points. That is 3,153. Then we can close here and load the raster file again. If we want to run a different simulation, we can run the script again. Then go here, simulation, single simulation. Then we can fill all this information again. Step 1, select the parameter, the cutoff, 1,250, lag distance, 100 meters, Nagar effect, 0.10, model spherical, range 1166.12, partial seal 129. Select the grid location, is this grid over here. Maximum number of samples, we say 150. And in this second case, we are not going to save the files. We are going to leave as a provisional one or temporary one. Then we can run this script again. And as you can see, the structure for the new simulation is the same as before. And also here at the bottom, we have the new simulation. We can take this one out. Even we can move this one to the top. This one is the one that we created, and this one is the second one. As you can see, this one has different range. This one goes from minus 3.48 to 3.48. But the first one goes from minus 3.62 to 3.38. And you can see that this one and this one has different values for each pixel. Now, if we run again the simulation, we are going to get a different one, that is this one. All of them are different. As you can see, when we take this one out, these values are different, and when we take this one out, the one at the bottom is different. Then every time we press the button run, we are going to generate a new simulation. However, it's not really practical to generate the simulations by one. That's the reason, because at the end of this video, I'm going to show you another script that can generate 10 simulations just with one click. You can modify that script to generate 20, 30 the simulations that you need for your project. Now I'm going to close this one here. I'm going to remove the provisional raster files and also the spreadsheets. This one, remove this one also. This one and this one here. No, this one and this one. Remove. And we are going to work with the first that we created. Then first, I'm going to change the colors to add the same colors as we have here. Then properties, single band pseudo color, and it's going to be the ramp known as a plasma, this one over here. Then apply and OK. Now we are going to make zoom to the layer, and we are going to add the Google satellite. Now here we have 4 different maps. Let me take this one out. We have the simple Kriging created with the transform values from the Gaussian anamorphosis. We have the variance map of the transform values, and we have the simple Kriging in the original scale after applying the back transformation. All these 3 maps were created at the second lesson of this course. And for today, we have the first simulation, that is this one. At the beginning of the video, I said that when we want to perform a conditional Gaussian simulation, we have to cover several steps. These steps were the exploratory data analysis, the variography analysis, the creation of the grid, and then the performing the simple Kriging. The 3 first steps are mandatory, but the last one is optional. To perform the simple Kriging, it's not a step that you have to do always, right? But it's pretty nice to have the simple Kriging in order to compare the simple Kriging with the simulations. For example, in this case, this one is the simple Kriging, and this one is the simulation. And at the end, what we want is that the simulation show a pattern that is similar to the simple Kriging. As you can see here, we have a dark part. Here we have more light parts, and that one can be reflected also on the simulation, indicating that the simulation is respecting the values at the sample locations. This is a visual way of verifying that the simulation is covering the first assumption related with the conditional Gaussian simulation, that is related to respect the values at sample locations. Also, we have to verify that the simulation is replicating the statistical properties and also the spatial structure of the original data set. And that's what we are going to verify a little bit later, because now what I want to do is to analyze the simulation model, as we did in the previous lesson when we was analyzing the simple Kriging model. In the previous lesson, we was working with this drawing to explain the simple Kriging model. What we have here is the black dots. They are the data set. In this case, could be the zinc concentration. With the red line, what we have is the simple Kriging model. But this model could be also the ordinary Kriging model. And with orange line, what we have is the reality. Then when we are using simple Kriging or ordinary Kriging, what we can see is when we are moving from one high value to low value in our data set, the transition in the Kriging model is pretty smooth. But that smooth is not realistic, because the reality is doing something like that. In the reality, the transition from here to here is not a straight line. It's changing the values a little bit. We pass from high value to low value, the same, but it's doing something like that. Then with simple Kriging, what we are doing is reducing the variance of the reality. And that happened because one of the assumptions related with the Kriging. The Kriging, the model, what it wants is to minimize the variance as possible. In that case, the predicted value less the real value has to be minimum. And because of that assumption, the variance is smaller in the simple Kriging than in the original data set. And that can be reflected when we compare the spatial structure of the original data set with the spatial structure of the estimation values using the simple Kriging or ordinary Kriging. As you can see over here, we have the spatial structure of the original data set. This data set is the Gaussian anamorphosis transformation. And what we can see here is that the seal, that is the semi-variance, is the summation of the nugget plus the partial seal. And in this case, it's going to be around 1.4 for the original data set. But what happened when we calculated the structure for the estimated values using the simple Kriging? What we can see is that the nugget effect plus the partial seal, that is the semi-variance, is going to be around 1. Then the difference between this one and this one is going to be 0.4. And that's the semi-variance that we are losing when we are applying the simple Kriging. Then when we are doing conditional Gaussian simulations, what we want is to preserve the original spatial structure in the simulations. Then we are going to create a simulation like this one. The number of simulations is infinite, right? There are infinite simulations that we can do with our data set. And each simulation is going to be different. But they want to try to replicate the reality. And with a lot of different simulations, what we can do is to quantify the uncertainty. And that's the goal of doing conditional simulation. As we can do different scenarios of the potential reality, where we are keeping the values at the observed locations, we are keeping the same spatial structure as the original data set, and also the statistics, the mean and the standard deviation, we can create prediction maps based on simulations that are more close to the reality. They are more realistic than the simple Kriging or ordinary Kriging. Now let's go to try to reproduce this scenario with our models. Then to do that one, we are going to use this plugin, that is the terrain profile. Then we are going to put this one here at the top. That is our original data set. Then we are going to add first the simple Kriging, then select the layer, add the layer, and we are going to keep this color. Also, we are going to add the simulation, but we are going to change the color for the simulation for a green one. Okay, and also we want to add our original data set. Then add here the data set, select the parameter. In this case, it's going to be the Gaussian anamorphosis transformation. Okay, but also we want to change the color for a black one. Okay, now we are going to create a cross section of our model. Then let me take this one out at the moment because I cannot see well the docs. And also I'm going to take this one out and the satellite imagery. Then I'm going to create here a cross section with several points from our data set. Then it's going to be this one here, this one, some of them, right? To compare the simple Kriging with the simulation. All these ones. And also what I'm going to do here, I want to reduce the buffer. I don't know if I can do now. Let me see. Yeah, it works. And the last point is going to be this one. Then as you can see over here, maybe I cannot see well this one here. Let me change the buffer. because I cannot see the data points. To 10 maybe? Okay, it's not working. As we change the buffer at the middle of the process, it's not showing now the data set. Then I'm going to run this one again. Going to select again different points. Then in this section, we have the red line, that is the simple Kriging model. And we have the green line, that is the simulation. The simple Kriging and the simulation, they are surface. The black line is the sample locations. And these sample locations is not a surface, it's just points at the space. Every time the black line changes the direction is because we have one sample. But also, if you see here at the top, you can see this red circle. That is the point where we are moving. As you can see on the top, as we are moving, the red dot is moving also. Then here we can see that the red line, that is the simple Kriging model, is pretty smooth. But the green line is showing a lot of variability. It's changing a lot the values of the pixels. And that's what we saw over here, right? We have the red line that is pretty smooth, and we have the black line that is changing a lot the variability of the values. That is reflected also here in this model. Another interesting thing that we can see over here is that the simulation is following the simple Kriging model. As you can see, the simple Kriging is going down, but the simulation also is going down. Here, the simple Kriging is going up, and the simulation is going up. Here, the simple Kriging is going down, and the simulation is going down, but here, the simple Kriging is going up, and the simulation is going up. Then the difference between the simple Kriging and the simulation is that the simulation is adding more variability to the values at the unsampled locations compared with the simple Kriging. Another very interesting thing is that at the sample location, the model related with the simulation has not the exactly values. Here, for example, we have a sample location, and the simple Kriging has the same value as the sample location, but the simulation has a higher value. Then the simulation respects the value at the sample location, but doesn't have identical value. Here we have another sample in this point, and the simulation and the simple Kriging has the same value, but the value at the sample location is a little bit smaller. Then we can check, for example, this one. This one again, the simple Kriging and the simulation has the same value at the sample location, but the value that we have at the sample location is a little bit smaller. Here is different. Here we have the sample location and the simple Kriging with the same value, but for the simulation, the value is a little bit low. Then has to be clear that in the sample location, the simulation doesn't has the exactly value, has a value that is similar, okay? And that's an important point. Now I'm going to close this model here, and I'm going to show you how you can see also the difference between the value at the sample location and the value at the simulation. For example, let's go to take this point over here. Then we select the layer, that is step 1. Then we go to information, and we can select this point. Then here you have the information related with this point. And as you can see, the value for the original data set is 1.49. Now, if we select the raster, now we can select the pixel and see the information on the pixel. And the information on the pixel is saying that the value is 1.35. Remember that this one, it was 1.49. Then the value is not the same, but it's pretty close, right? With 1.49. Then we can check a different one. Sometimes the values are going to be more close, and sometimes the values are going to be more different. Let's go to select, for example, this one. And here we have a value of minus 1.75. And for the pixel, we have minus 1.48. As you can see here, the difference is 0.3, is bigger than before. But again, at the sample location, we don't have the exactly values in the simulation. We have values that are close. The values on the simulation and the values on the original data set are close enough. Then we can say that the simulation is respecting the values at the sample locations. Now the next step is to check if the simulation, the statistics of the simulation is replicating the statistics of the original data set. Then to do that one, we're going to create the histogram of the simulated values. Then let me close this one here. Go here, and we are going to use this histogram over here. Here, the layer that we have to add is the step 2 related with the simulation. Be careful, don't add here the step 2 related with the simple Kriging. Is this one, okay? Then we have to load the new one. Then we can add here this one. It's going to be the limited test. And it's going to be here in simulation. Data set is this spreadsheet. Open. Make sure you have to select this option. It is point coordinates. X field has to be with the X, Y field has to be with the Y, and this one is the information that we are going to add. Add and close. And as you can see now, is this green dots over here. Then here we are adding that one. Step 2, sim. The parameter is going to be this one. Label X is going to be the zinc concentration. But remember that this zinc concentration is related with the Gaussian anamorphosis transformation. It's not the original zinc concentration in ppm. The label Y is going to be the frequency. That is the frequency, that is the number of samples. The title of the graph could be the histogram. The subtitle could be Gaussian anamorphosis transformation. The minimum value is the value that we have here. The minimum value is, we can see that one in the range. The minimum is minus 3.628636, and the maximum is this one, 3.382676. And the number of bits in this case is going to be 12. I'm putting 12 here because I'm going to compare this histogram that it comes from the simulation values with the histogram that we can get with the original data set, with the transformed data with the Gaussian anamorphosis. Now we can run this script and double click to open. We can make this screen bigger. And as you can see here, we have a perfect Gaussian distribution. Also, we have a mean and median that are located in the same position, and they are very close to 0. And also a standard deviation of 1. Now, I am going to take this histogram but I'm going to change the title because here I want histogram simulation, and I'm going to compare this one with the original data set and also with the simple Kriging results that we get on the estimation for the distribution. I'm going to prepare that slide and I'm going to show you right away. Here we have the first histogram related to the original data set. In this case is the Gaussian anamorphosis transformation for the zinc concentration. And here we have the distribution. We have a mean of 0, a median of 0, and a standard deviation of 1. This one is for the histogram for the estimation using the simple Kriging. Then here we have all the unsampled locations. Then the distribution is showing a mean of minus 0.26, a median of minus 0.3, and a standard deviation of 0.86. And also the shape looks pretty normal distributed, but here we have a peak. Then if we compare the simple Kriging with the original data set, we can see that the mean and median and the standard deviation are a little bit different. This histogram is from the simulation. Here we have a perfect Gaussian distribution as we have over here. And also the mean and the median, they are pretty similar. Here in the simple Kriging, they are a little bit different. Not that much, but just a little bit. But here they are almost at the same location. And in both cases, they are not 0 as the original data set, but the simulation is closer to the original data set. Because here the mean is a little bit smaller than here, and also the median is a little bit smaller than here. And the standard deviation here practically is identical to the original data set, while here is a little bit different. With respect to the range of values, what we can see is that the simple Kriging is closer to the original data set. But in the simulation, we have a minimum that is smaller and maximum that is bigger. But that is normal because what we want with the simulation is to add variability to the model. And that's the reason because we have a different range. Then in general, we can say that the histogram from the simulated values at the unsampled locations is covering the assumption of replicating the statistics of the original dataset, because we have a mean, a median, and a standard deviation that they are very similar to the original dataset. Now, the next step is to see what's going on with the spatial structure of the simulated values at the unsampled locations. Then to do that one, let's go to create the semi-variogram model. It's going to be the script, this one here, the 19.2. Then again, we are going to select the step 2 simulation. The parameter is going to be this one. We are going to add the same values for the semi-variogram as we did with the simple Kriging. 1250. The lag distance is going to be 100. Initially, I'm adding these values to see how it looks like, okay? Then the seal is going to be, that is the partial seal, is going to be 1.29. The model is going to be the spherical. The range is going to be 1176.12. And the negative effect is going to be 0.10. Now I'm going to add all the labels, but I'm going to pass the video faster. I already added all the labels. For the label X is the lag distance in meters. For the label Y is the semi-variance of the zinc concentration for the Gaussian anamorphosis transformation. The title of the graph is going to be the SIM spherical model for zinc. And subtitle is going to be Gaussian anamorphosis transformation. And I'm going to save in this folder. Then now I'm going to run the script. And as you can see, we have the structure for this model over here. We have an aggregate effect that is 0.10. We have a partial seal of 1.23 and a range that is 1086. It's a little bit less than the values that we have for the original data set. I mean for the range, because the original data set, the value it was 1176, and in this case we have 1086, and the partial seal is a little bit smaller because we have 1.23, and in the original data set what we have is 1.29, but it's not that difference, right? Then double click to open, and now we can make this screen bigger. What we can see is that we have a model that fits really well on the data, most in the beginning of the semi-variogram. This is the most important area of the graph because it's where we have the spatial correlation of our data. Here at the top, the fit could be a little bit better, but it's not that bad. Also, what we can see is that we have a very robust semi-variogram with a lot of pair of points for each lag. Now, what we are going to do is compare this structure from the simulation with the simple Kriging and with the structure of the original data set, as we did with the histograms. I'm going to show you the slide right away. Then here we have the three models. This one is for the original data set for the Gaussian anamorphosis transformation data. Remember that this one is 155 samples, and we get this structure over here. This one is for the simple Kriging for the unsampled locations. In this one, we have 3,153 samples, and this one is the structure. And this one is for the simulation. We have the same number of samples as here for the unsampled locations, and this one is the structure. As you can see, the structure for the simulation, it's pretty similar as the structure that we get on the original data set. Even the values are almost the same. However, for the simple Kriging, at the lesson 2, when I was trying to fit the model on the data, to keep the spherical model, it was even pretty complicated, right? The fit, as you can see, also is not the best. The range could be approximately the same for all of them, but as you can see, for the semi-variance, this one has a very low semi-variance, that is around 1. But for the original data set, the semi-variance is around 1.4. And that's the semi-variance that we get also here, right? It is 1.33. Then we can say that the structure of the simulation is replicating the structure of the original data. Then at the end, we have a simulation that is pretty good because it's preserving the values at the sample locations. We know it is not the same values, but it's pretty similar. We are preserving the statistics of the original data set, and also we are preserving the spatial structure. Now, the next step is to revert let me close this one and this one. Let me zoom on this layer. And let me take this one out. And let me put the Google satellite. The next step is to revert the simulation to the original scale. We want to see the pixels that is showing the concentration of the zinc in ppm. Now the pixels is showing the concentration in the Gaussian anamorphosis transformation. Then to do that one, we are going to use the same script that we was using to revert the simple Kriging. Then it was the step number 3. Back transformation Gaussian anamorphosis. Then we can open this one. If you want to know how this script works, my recommendation is to watch the second lesson of this course about the simple Kriging. In that lesson, we explain how this script works because it's a little bit complicated, okay? Then first, what we have to add here is the original data set, the Muse River data set. Then the original parameter is the zinc concentration. The x-coordinate has to be the x-coordinate in that data set. The y-coordinate has to be the y-coordinate. The number of polynomials has to be the same that we was using when we created the Gaussian anamorphosis for the simple Kriging. Then the layer Gaussian has to be the step 2 for the simulation. This is important, okay? Don't take the step 2 for the simple Kriging. It has to be the simulation. Then again here, for the parameter, the Gaussian one has to be the values at the unsampled locations. Then the x-coordinate has to be the x-coordinate, and the y-coordinate has to be the y-coordinate. This script is going to generate an spreadsheet, and in that spreadsheet we are going to have the x and y coordinates for each unsampled location, and also is going to have the variable that goes back with the Gaussian anamorphosis transformation. Then we have to save that spreadsheet. Then here, go to simulation, and here in this folder, in dataset, I'm going to save this one as a step 3 simulation. Then save, and now we can run this script. Now we can go here to the folder, simulation, this one here, dataset, and here we have the step 3, and we can open. Okay, open as a copy or just for read. And here what we have is the x and y coordinates, and now here we have the concentration of sin in ppm. We already back to the original scale, and we have these values for all the unsampled locations, the 3,153 points that we have in our grid. Then we can close this one, we can close the other one also, and now we are going to create the raster. Then we can close this one and open the next script, that is the step 4, final raster, original scale. Then double click, and here what we have to add is just that spreadsheet. Then go here, go to the simulation, this one, dataset, step 3, open, and also we can save the raster, save, and we have here a raster, single simulation. Yeah, here I'm going to add original scale. Then that's it, save, and now we can run this one. Remember that this script, the step 4, was also created at the lesson number 2 when we was talking about simple Kriging. Then now we can close this one, and we can add the same colors as this one. Then open, go to properties, single band pseudo color, and select the plasma ramp, apply, and OK. We can add here the reference coordinate systems, that is the 28992. OK. And also we can check the range. Here we have the minimum value is 113 and the maximum value is 1848. With the simple Kriging, this one over here, the simple Kriging, but when we revert the Gaussian anamorphosis, then in this case we have the minimum value 115 and the maximum value 1727. Then you can compare these values, and you can see that here the maximum is a little bit higher and the minimum is a little bit smaller than the results that we get in the simple Kriging. Also, we can compare the values that we get, the range that we get in the simulation with the values that we have in the original Muse River dataset. Then we can open the attribute table, and we can see here that the minimum value for the zinc concentration is 113, and the maximum value for the zinc concentration is 1,839. Then the range that we have in the Muse River dataset is pretty close at the range that we have with the simulation, even is closer than the range that we get with the simple Kriging. In addition, we can compare visually the simulation, that is this one, with the simple Kriging, that is this one, for the original scale both. This one is the simulation, and this one is the simple Kriging. We can see also here that the simple Kriging is very smooth, right, because of the transition of the colors. But the simulation is more, the values are more random. Then the last thing that we are going to do is just, I'm going to show you the script that I created to create 10 simulations at once. But first, let me change the name of this script. Then edit script. Here, save as, and in this case, it's going to be a step 2 single simulation. Then we can save, close this one here. Now, if we go to R, simulations, we can remove this one, delete script. Then for the step 2, as you can see now, we have the simple Kriging and also the single simulation. Now I am going to create a new script for the 10 simulations at once. Then the interface is going to be the same as the one we have for the single simulation. This is the libraries that we are going to use. All the things are the same as the single simulation. The only thing is changing is, in this case, we are specifying that we want 10 different simulations. And I designated that simulations as a simulation 1, simulation 2, until simulation 10. Then this script is going to generate 10 different rasters with the simulations, and also is going to create the spreadsheet. In the spreadsheet, we are going to have the values for the simulations in all unsampled locations. Then I'm going to save this script with this name, step 2, 10 simulations. Then I'm going to cut this one here, remove these 2 rows, save as, and we can paste here that name. Then save and close. Remember that in the lesson 2, when we was talking about simple Kriging, we said that we are going to organize the Gaussian anamorphosis transformation and revert the Gaussian anamorphosis in 4 steps, right? The step 1 is to do the Gaussian anamorphosis. The step 2 is to do the simple Kriging or the simulation with the Gaussian anamorphosis. And that's the reason because I have the step 2 for the 10 simulations, step 2 for the simple Kriging, and step 2 for the single simulation. Then the step 3 is to revert the Gaussian anamorphosis to the original scale. And the step 4 is to create the raster with the original scale. That's the 4 steps that we have to follow when we are doing simple Kriging or when we are doing a simulation or several simulations. Now let's go to test the new script, the 10 simulations. Then double click to open. And here we can add the parameters. First has to be the step 1, because the step 1 has the values for the Gaussian anamorphosis. Then we have to select this one. And now we are adding the parameters as we did for the single simulation. Remember that these parameters were calculated in the lesson 2 when we was working with the simple Kriging. Then I refer it 0.10. The model is going to be the spherical. The range is 1176.12, and the partial C is 1.29. The grid location is here, simple Kriging, data sets, grid points is this one, okay? Maximum number of samples, we are going to use in this case 150, as we did previously. And now, as you can see, we can save the 10 simulations from 1 to 10. Then we have to select the folder where we want to save that simulations. Says file. It's going to be in this folder in rasters. And in this case, it's going to be simulation number 1. I'm going to do the same for the rest of the simulations, but I'm going to pass the video faster. I added already all the links, and now we are going to save also the spreadsheet. Remember that this spreadsheet is going to show the X and Y coordinates and the values for all the simulations at the unsampled locations. Then we are going to save this file. The folder simulation is going to be data sets, and in this case is going to be step 2, this one, but 10 simulations. I'm going to add 10 simulations here at the beginning. And also this one here, and save. And now we can run this script. We can close these windows. And as you can see, now we have from simulation 10 is over here, 1 is over here, from 1 to 10 simulations. Then as you can see, if we check this one, you are going to see that the simulation at the bottom is different always. Then we have in total 10 different simulations. Also has been now added the table with the information. We can open this attribute table, and as you can see, we have the X and Y coordinates, and for each of the simulations, we have the simulated value. But also we have that information in an spreadsheet. Is this one over here. Step 2, 10 simulations, double click to open. Okay. Open copy. And as you can see, we have the same information, the X and Y coordinates with the 10 simulations. Remember that we can use this data to create the histogram with the simulated values for the unsampled locations, and also the structural analysis, right? To see how the model fits on the semi-variogram, to verify that these simulations are replicating the information that we have in the original data set. Now with the next script, that is going to be the step number 3, we are going to take all these values that are in the Gaussian anamorphosis to go back to the original scale. Then we are going to create an spreadsheet where it's going to show the X and Y coordinate and also the simulations and the original scale for each of these unsampled locations for all the simulations. Then we can close this one here, go here to new script, and I'm going to paste what I did already. Paste. And I'm going to save with this name, step 3, 10 simulations, back transformation, Gaussian anamorphosis. Then I'm going to cut this one here. And I'm going to remove these 2 rows. And save here. Remember that this script is the same that we was using for simple Kriging, right? But in this case, what we are adding is the 10 different simulations. If you want to know how this script works, just my recommendation is to watch the second lesson of this course, where this script was explained. Then we can close this one here. And now we can run the script. Simulation, Step 3, 10 simulations, back transformation of the Gaussian anamorphosis. Here we have to add the original Muse River data set with the original parameter, that in this case is the zinc concentration. Here we want to add the X coordinate, and here we want to add the Y coordinate. Number of polynomials is 43, as before. Here, in this one, we have to add the step 2 for the 10 simulations, but we didn't load it here. We have here the table, but we have to add the CSV file here. Then go here, select the limited test, look for that file, simulations here, data set. That's the spreadsheet that we have to add here. Open. Make sure you have selected this option. Y coordinate, X field has to be with the X coordinate, Y field has to be with the Y coordinate, and here we have the attribute table, or the table that we are going to add in QGIS. Then add and close. And as you can see, this information is all these docs that we can see here at the back. And that's the information that we want to add here. Step 2, 10 simulations. Then here, simulation number 1 is this one. This one is the one that is loaded already here at the panel. Then we have to select the coordinates, coordinate X and coordinate Y. And now we have to add all the simulations. Number 2, number 3. And I'm going to pass the video faster. Now also we have to save the spreadsheet that this script is going to create with the values in the original scale, with the sync in ppm. Then let's go to select a file, simulation, data set, and it's going to be this one, step 3, 10 simulations. Here I'm going to add the 10 simulations here. Then save. And now we can run this script. Now, as you can see, we have a new table. Step 3, 10 simulations. We can see the table. And here what we have is the X and Y coordinates. And for X simulation, we have the values in the real scale. This scale already is in ppm. Then we can close this one here, and we can verify that we have that information also here. Step 3, 10 simulations, open, open, open as a copy. And as you can see here, we have the same information, the X and Y coordinates and the 10 simulations. It is interesting that for each row, we can see how the value of the pixel is changing in each simulation. That is showing the great variability of all the X scenarios that you can create with the different simulations. Now we can close this one and go to the last thing. As you can see, this script doesn't load any raster file. It's loading just this table over here. Then with the next script, what we are going to do is take all that data to create the rasters in the original scale. Then go here to R, create a new script. I'm going to paste here what I did already. I'm going to save this script with step 4, 10 simulations, final raster, original scale. Then I'm going to cut this one here, remove these 2 rows, and I'm going to save this one here. Save. And again, this script was already explained in the second lesson when we was talking about simple Kriging, because we use the same script. The only thing is changing that here we are adding the 10 simulations. Then we can close this one here. And let's go to check the script. Simulation. Step 4, 10 simulations, final raster, original scale. Then double click to open. And here in back transformation table, we have to add the step 3. Then go to here, simulation, this one, data set, and step 3 for the 10 simulations is this spreadsheet. Then open, and here we have to select where we want to save the new raster files. Then that ones are going to be saved in the folder for rasters, and it's going to be designated with number 1 for the original scale. Then save, and I'm going to do the same for the rest of the simulations, but I'm going to pass the video faster. Okay, I did already, and now we are ready to run this script. And as you can see, it has to be something wrong because the layers has not been generated. Then if we go up, we can see the error is because the object X not found. Then the problem is the script. Let me show you here, edit the script, and it's related with this line over here. What this line is doing is removing the first column. But if we check the spreadsheet, the first column is the X. Then we are eliminating this column, but we need this column to do the rasters. And then we have to eliminate this line here from the code. Because when I design this script, at the first column, I have an ID for each point. But now in this spreadsheet, I don't have longer that ID. Then I don't want to use that line to remove the first column. Then we remove this one already. We save the script. And now we can try again. But as we make a modification, we have to add again all the where we want to save all the rasters. Then I'm going to save that ones, but I'm going to pass the video faster. Now we can try to run the script again. Now, as you can see, we have the 10 simulations with the original scale. Is simulation 5 original scale, as you can see over here. What happened that we have to add the reference coordinate systems for each simulation. Then, for example, if we want to edit this one with the same colors as we have for the other ones, then go to single pseudo color, the plasma ramp is this one, apply, and OK. We can close this one here, and this simulation is with the same colors as the other ones. As you can see, each simulation is different, right? Because when I take this one out, you can see that the simulation at the bottom is different. Well, that's it for this lesson. Thank you very much for watching it, and see you on the next lesson.